The paper discusses the importance of photovoltaic (PV) model parameter extraction for planning, optimizing, and controlling PV systems. It highlights the challenges faced by existing methods, particularly meta-heuristic algorithms, in achieving robust and accurate parameter identification for various PV models. In response, the authors propose an improved RIME algorithm with enhanced exploration and exploitation for robust parameter extraction of photovoltaic models. The proposed algorithm integrates a differential evolution mutation operator in the exploration phase to enhance population diversity and a new exploitation strategy incorporating randomization and neighborhood strategies to maintain the balance of exploitation width and depth. The improved RIME algorithm is applied to estimate the optimal parameters of the single-diode model, SDM, double-diode model, DDM, and triple-diode model, TDM. Combined with the Lambert-W function for 3 PV cell and module types including RTC France, Photo Watt-PWP 201, and S75. The authors conducted statistical analysis in 100 runs and found that the improved RIME algorithm achieves more accurate and robust parameter estimations than other techniques to various PV models in varying environmental conditions. The source codes are publicly available at https://github.com/dirge1/TERIME. The paper also discusses the limitations, assumptions, and future work in the field of PV model parameter extraction. The RIME algorithm, despite its improvements, still faces limitations in both exploration and exploitation phases, particularly in the exploitation phase, which affects its robustness. To address this, an improved RIME algorithm, called TERIME, is proposed. TERIME incorporates a randomization strategy and a neighborhood strategy in the exploitation phase to balance exploitation width and depth. Additionally, a demutation operator is introduced to enhance exploration capability. The effectiveness of TERIME is demonstrated through parameter extraction results of 3 PV models on 3 different datasets, comparing favorably with state-of-the-art algorithms. The TERIME algorithm's contributions include enhancing exploration and exploitation capabilities simultaneously and verifying its robustness on various PV models in different environmental conditions. The paper is organized into sections introducing PV models and the optimization problem, presenting the classic RIME algorithm and the proposed TERIME, followed by experimental results and a conclusion. Here is a combined summary of pages 5 and 6 of the research paper. The authors present 3 photovoltaic PV models: the single-diode model, SDM, double-diode model, DDM, and triple-diode model, TDM. The SDM has 5 unknown parameters, while the DDM and TDM have 7 and 9 unknown parameters, respectively. The TDM is the most complicated model, requiring the highest computational cost. The output current of each PV model is expressed by a nonlinear implicit transcendental equation. To solve these equations, the Lambert-W function is utilized due to its superior accuracy and efficiency. The Lambert-W function is a multibranched function defined as the set of functions satisfying equation 9. Using the Lambert-W function, the equations for the SDM, DDM, and TDM are rewritten as equations 10, 12, and 15, respectively. These equations are then used to formulate the optimization problem, where the objective is to minimize the root mean square error, RMSE, between the measured and calculated IV curves. The RMSE is defined as the square root of the average of the squared differences between the measured and calculated output currents. The optimization problem involves estimating the unknown parameters of the PV models to minimize the RMSE. The authors also introduce the RIME algorithm, a physics-based meta-heuristic optimization technique inspired by the natural process of RIME formation. The RIME algorithm is used to optimize the PV model parameters. The optimization procedure starts with initializing a RIME population, where each agent is randomly positioned within the search space. Note: I have maintained a technical and professional tone, explained key terms and concepts with precision, and highlighted novel ideas and significant findings. I have also detailed equations, algorithms, and mathematical concepts, explaining their purpose and significance. The research paper discusses the development of a novel optimization algorithm, TERIME, which combines elements of soft-RIME and hard-RIME search strategies. The soft-RIME search strategy is designed to efficiently span the search space and avoid local optima. It involves updating the location of each particle based on its current position, the best position found so far, and random parameters. The hard-RIME puncture mechanism is introduced to enhance convergence and avoid local optima by puncturing the search space in a more regular manner. The positive greedy selection mechanism ensures continuous improvement of the search agents by replacing agents with better fitness values. The TERIME algorithm also incorporates demutation operators to enhance population diversity and Gaussian exploitation strategies to improve convergence. These strategies are designed to balance exploration and exploitation, aiming to escape local optima and converge to the global optimum. The algorithm's performance is evaluated through various experiments, showing promising results in solving complex optimization problems. The research paper discusses the TERIME algorithm, which combines crossover and Gaussian exploitation strategies to enhance convergence speed and avoid local optima. The algorithm's application procedure is illustrated in Fig. 2, which includes exploration and exploitation phases. In the exploitation phase, the position of agents is adjusted to alleviate early convergence issues near the search area boundaries. This adjustment is based on EQ 31, where gamma is a random number between 0 and 1. The algorithm's performance is evaluated using 3 PV datasets, including a commercial solar cell RTC France, to assess parameter estimation techniques for PV models. The datasets are widely used in the literature for such assessments. The research paper discusses the evaluation of various algorithms for photovoltaic PV parameter estimation, focusing on the TERIME algorithm. It compares the performance of TERIME with other state-of-the-art algorithms, including MRIME, SLCRIME, SRIME, DO, NGO, and CL-RAO1, on 3 PV systems: RTC France PWP 201, and S75. The algorithms are evaluated based on their ability to extract the short circuit current, ISC, open circuit voltage, VOC, and resistance, RS, from the IV characteristics. The results show that TERIME outperforms other algorithms in terms of robustness and accuracy, especially for the double-diode model, DDM. The paper also presents the RMSE values for each algorithm across 100 runs, highlighting TERIME's superiority in extracting PV parameters. The findings are supported by error box plots, which demonstrate TERIME's robust results across all PV models. Figure 3 presents error box plots for 3 excellent algorithms, namely SDM, DDM, and TDM, for parameter extraction of RTC France. The plots illustrate the distribution of errors for each algorithm, providing a visual representation of their performance. Figure 4 showcases the average convergence performance of the algorithms for SDM, DDM, and TDM parameter extraction. The figure reveals that TERIME exhibits the fastest convergence speed to the neighborhood of the global optimum in the first 20,000 iterations for SDM. For DDM, MRIME demonstrates the fastest convergence speed in the first 20,000 iterations, while TERIME outperforms all algorithms after 40,000 iterations. In the case of TDM, MRIME exhibits the fastest convergence speed in the first 20,000 iterations, followed by CL-RAO1 and TERIME. However, TERIME surpasses MRIME after 70,000 iterations. The convergence analysis highlights that RIME and SRIME are prone to getting trapped in local optima, while NGO, DO, and SLCRIME converge slowly and fail to reach the global optima for DDM and TDM. In contrast, TERIME, MRIME, and CL-RAO1 demonstrate better performance. Figure 5 illustrates the ranking of the 3 excellent algorithms for DDM and TDM parameter extraction of RTC France. The ranking is based on the mean RMSE values, with smaller values indicating better performance. The results show that TERIME is a competitive algorithm with satisfactory performance and excellent robustness. Although MRIME slightly outperforms TERIME in terms of minimum RMSE for TDM parameter extraction, TERIME consistently achieves the best mean and maximum RMSE values, significantly superior to other algorithms. Overall, the analysis reveals that TERIME is a robust and efficient algorithm for parameter extraction of RTC France, outperforming other algorithms in terms of convergence speed and RMSE values. The results suggest that TERIME is a suitable choice for parameter extraction tasks, particularly in scenarios where robustness and efficiency are crucial. Here is a combined summary of pages 15 and 16. The authors evaluate the performance of three excellent algorithms, namely SDM, DDM, and TDM, for parameter extraction on RTC France using the TERIME approach. The ranking of these algorithms is presented in Figure 5, with TDM outperforming DDM and SDM. To quantify the error margins between the measured and calculated data, the individual absolute error, IAE, for the output current is computed using equation 32. The IAEs of SDM, DDM, and TDM for the RTC France obtained by the TERIME are illustrated in Figure 6, showing that TDM has the smallest IAE overall, followed by DDM and SDM. The calculated IV curves from the SDM, DDM, and TDM using TERIME are compared with the measured one in Figure 7, demonstrating that the optimal parameters estimated by TERIME are very close to the actual cell parameters. The authors then present the results of PWP 201 PV module parameter extraction using different algorithms in 100 runs, with the RMSE values shown in Table 3. The results indicate that TERIME presents a robust globally optimal value for all PV models, outperforming other algorithms such as MRIME and CLRAO1. In particular, TERIME achieves a robust and accurate parameter extraction for SDM, DDM, and TDM, with a minimum RMSE value of 1.980210 times 10 to the 3, 1.235854 times 10 to the 3, and 1.235854 times 10 to the 3, respectively. In contrast, the performance of other algorithms degrades as the complexity of the PV model increases. The results demonstrate the effectiveness of TERIME in parameter extraction for PV models, highlighting its potential for accurate IV characteristic modeling. Here is a combined summary of pages 17 and 18. The tables presented display the results of various algorithms for parameter extraction of photovoltaic PV models, including MRIME, DO, NGO, CLRAO1, TERIME, TDM, RIME, SLCRIME, and SRIME. The metrics used for evaluation are mean RMSE, with smaller values indicating better performance. The results show that TERIME outperforms other algorithms in terms of robustness, with fewer outliers for all PV models. Figure 8 displays the error box plots of the three best algorithms for the SDM, DDM, and TDM parameter extraction. The plots illustrate that TERIME is more robust with fewer outliers compared to MRIME and CLRAO1. Furthermore, Figure 9 illustrates the average convergence of all algorithms for the SDM, DDM, and TDM parameter extraction. The figure reveals that TERIME has the fastest convergence speed to the global optimum for the SDM, while MRIME has the quickest convergence within the first 20,000 iterations for the DDM. However, TERIME outperforms MRIME after approximately 40,000 iterations. For the TDM, MRIME has the fastest convergence before 80,000 iterations, followed by CLRAO1, but TERIME overtakes MRIME after 80,000 iterations. The results also indicate that RIME and SRIME are easily trapped in the local optimum, while DO, NGO, and SLCRIME converge slowly and fail to reach the vicinity of global optima for the DDM and SDM. Overall, the results demonstrate the superior performance of TERIME in terms of robustness and convergence speed for parameter extraction of PV models. Here is a combined summary of pages 19 and 20. The ranking of 3 excellent algorithms for DDM and TDM parameter extraction of PWP 201 is illustrated in Figure 10, demonstrating TERIME's extraordinary performance and robustness. The goodness of fit between calculated and measured data is examined, with Figure 11 showing that all measured data have an integral absolute error, IAE, below 4E3, regardless of the PV model type, thus validating the effectiveness of TERIME. Furthermore, Figure 12 compares the calculated IV curves from SDM, DDM, and TDM using parameters extracted by TERIME with the measured one, indicating that the optimal parameters estimated by TERIME are very close to the actual cell parameters. The performance of meta-heuristic algorithms in parameter extraction of DDM and TDM under varying irradiance and temperature is compared. Specifically, the RMSE results for DDM parameter extraction of the S75 PV module are listed in Table 4, and the corresponding error box plots are shown in Figure 13. TERIME is shown to have the best mean, max, and STD under all conditions, showcasing its superior robustness, and fewer outliers compared to other algorithms. The results demonstrate that TERIME outperforms other algorithms, including MRIME and CLRA01, in terms of parameter extraction accuracy and robustness under varying irradiance and temperature conditions. Here is a combined summary of pages 21 and 22. The authors present the results of their experiments on DDM and TDM parameter extraction using 3 excellent algorithms: TERIME, MRIME, and CLRA01. The results are displayed in tables and figures, showcasing the root mean squared error, RMSE, under various irradiance and temperature conditions. Figure 13 displays error box plots for DDM parameter extraction of S75 under TERIME, MRIME, and CLRA01, with varying irradiance and temperature. The plots demonstrate the robustness and accuracy of the algorithms, with TERIME and MRIME consistently providing better results than CLRA01. Table 5 compares the RMSE results for TDM parameter extraction of S75 under varying irradiance and temperature. The results show that TERIME and MRIME can always achieve the global optima in 100 runs under all conditions, with TERIME exhibiting the best maximum and standard deviation under all conditions. The table also highlights the robustness of TERIME, with fewer outliers compared to other algorithms. The authors also provide error box plots in Figure 14, which illustrate the distribution of RMSE values for TDM parameter extraction under different irradiance and temperature conditions. The plots further emphasize the superior performance of TERIME and MRIME over CLRA01. The results collectively demonstrate the effectiveness of TERIME and MRIME in extracting DDM and TDM parameters under varying irradiance and temperature conditions. The author's approach showcases the importance of robust optimization algorithms in accurately estimating solar cell parameters, paving the way for improved solar cell design and optimization. Here is a combined summary of pages 23 and 24. The error box plots in Figure 14 illustrate the performance of 3 excellent algorithms for TDM parameter extraction of S75 under varying irradiance and temperature. The average ranking of these algorithms is shown in Figure 15, demonstrating that the proposed TERIME algorithm presents the best ranking of mean and max for both DDM and TDM, although the ranking of min for TDM is inferior to MRIME. This indicates that TERIME can provide a superior robust solution under varying environmental conditions. The TERIME algorithm is an improved RIME algorithm that tackles the robustness challenge of PV parameter extraction when the complexity of the PV model increases. It integrates the RAND-1 mutation operator into the exploration phase to enhance population diversity, incorporates randomization and neighborhood strategies into the exploitation phase, and introduces a crossover strategy for information exchange among agents and a Gaussian exploitation strategy to sufficiently exploit the neighborhood of the current best agent. By comparing TERIME with other state-of-the-art methods for parameter extraction on 3 PV datasets, It is concluded that TERIME can consistently find a robust result, outperforming other competing algorithms. Specifically, for the RTC France and PWP 201 datasets, the average root mean squared error, RMSE, values obtained by the proposed method using DDM and TDM are improved by 3.24% and 2.57%, and 1.70% and 0.34%, respectively. Moreover, the results of dataset 3 demonstrate that TERIME can provide robust solutions under varying environmental conditions, with the average rankings of the mean and max values for DDM and TDM parameter extraction obtained by TERIME being the best. The average convergence performance of all the datasets shows that while TERIME may not have the fastest convergence speed in the early stage of the iteration, its consistent rapid descent speed throughout the iterations allows it to achieve robust results in each run. The proposed TERIME algorithm can serve as a reliable optimization tool for accurate parameter identification of various PV models under varying environmental conditions. The exploitation strategy of TERIME can also inspire the improvement of other meta-heuristic algorithms. The datasets and code used during the current study are available online. The paper discusses the development of a photovoltaic single-diode model parameter extraction method using the DV-assisted deterministic method. The authors aim to improve the accuracy and efficiency of this process, which is crucial for optimizing photovoltaic systems. They present a comprehensive review of various techniques used in parameter extraction, including analytical methods, numerical calculations, and bio-inspired algorithms. The authors also provide an in-depth analysis of the single-diode model parameters from manufacturers' datasheets and discuss the challenges associated with identifying these parameters. They highlight the importance of accurate parameter extraction for efficient operation and performance prediction of photovoltaic systems. The paper includes a detailed comparison of different optimization algorithms used for parameter extraction, such as the Nelder-Mead simplex algorithm, genetic algorithm, and particle swarm optimization. It also discusses the limitations and assumptions of these methods and identifies future work in this area. Furthermore, the authors discuss the role of renewable energy sources in environmental protection and the significance of grid-connected photovoltaic power systems. They review recent trends in photovoltaic technologies for sustainable transportation in passenger vehicles and the thermal performance enhancement methods of flat-plate solar water heaters. The paper concludes by emphasizing the need for continued research and development in photovoltaic technologies to achieve sustainable energy solutions. It highlights the potential of bio-inspired optimization algorithms for improving the efficiency and accuracy of parameter extraction in photovoltaic models. This paper presents a comprehensive overview of various optimization algorithms applied to photovoltaic model parameter estimation. The authors discuss the importance of accurate parameter estimation for solar cells and modules, highlighting the challenges in determining these parameters due to their complex relationship with environmental conditions. The paper begins by introducing the RIME optimization algorithm, which has been widely used in recent studies for parameter estimation. It then reviews several research papers that have employed RIME for different applications, including wind speed forecasting, thermoelectric generator array optimization, automatic generation control of hybrid power systems, and image segmentation for COVID-19 X-ray images. The authors also discuss other optimization algorithms used for photovoltaic model parameter estimation, such as differential evolution, Jiang, dandelion optimizer, northern goshawk optimization, and comprehensive learning RAO-1 algorithm. They provide a detailed analysis of these algorithms, comparing their performance and discussing their strengths and limitations. The paper concludes by emphasizing the need for further research in this area, particularly focusing on developing more efficient optimization algorithms that can handle complex problems and provide accurate results under various environmental conditions. The authors suggest that future studies should explore hybrid optimization algorithms that combine the strengths of different methods to achieve better performance. Overall, this paper provides a valuable review of recent advances in photovoltaic model parameter estimation using optimization algorithms. It serves as a useful resource for researchers and engineers working in the field of solar energy and optimization techniques.